So in this topic, let's consider a satellite going around uh, a static star. And on that satellite, we put a gyroscope, okay? And so the gyroscope will have a certain heading. It's characterized by a certain spin direction. And let's see how that spin direction correlates with the vector that points out the position of the satellite itself as it orbits around the star. Okay. Again, this will give us a measure of the character of the space-time around the star, and it provides a very important test of general relativity. Okay. And in this case, we'll be interested in applying the idea to a strong gravity as well as weak gravity. Remember when we did the lens tearing precession? That was the precession where we have a correlation between the rotation of a star and the orientation of the spin of a gyroscope. That we could get that result from weak field gravity. And here I want to be more general and do the full case. And so I'll use the Schwarzschild solution to describe the static star. Okay, so not a rotating situation. Okay, just a situation with a Schwarzschild metric, and it'll demonstrate some of the ideas of curved space-time. Okay, so here we go. Imagine gyroscope in orbit around the Earth, well, some planet or some star where the rotational angular momentum is not significant. Okay. How is the gyroscope spin correlated to the orbital motion? Well, if we were doing this is a problem with Newton. It wouldn't really be that interesting because in Newton's world, space-time is not curved. Okay, time is universal, and we'll see there won't be any effect. That the gyroscope spin will just maintain its particular initial orientation as the body orbits. Okay. Okay. So the body itself moves along a geodesic, and I write it down like that. And I'm going to write it down in Schwarzschild coordinates. So my velocity has a time component, a radial component, a theta component, and a phi component. And we'll use what we know about the orbits of bodies in the Schwarzschild metric to simplify the problem. Okay, and we studied that problem quite thoroughly. We did the equivalent of the Kepler problem for Schwarzschild, and we have a lot of the answers already for us, and we'll go back to our discussion of the orbits and the Schwarzschild metric and steal them. Okay, well that characterizes the body, but now I want to think about the spin. Okay, so I have a spin 4 vector. Okay, and I know what that means. If I take the gyroscope and sit in its rest frame, the spin points in a particular direction. I can move the gyroscope around. Okay, and in those situations, that spin will stay in that direction as I move the body under it. Okay. And so clearly the dot product of the 4 vector describing the spin, okay, and the 4 vector describing the velocity of the body are orthogonal, okay, because in the rest frame, U is purely time-like, S is purely space-like, and I get 0 just trivially. But that's going to be true in every frame, and it'll be instructive to write down this identity, okay, in the Schwarzschild coordinates. Okay. And so I see in particular that S dot U is equal to 0, and that's true for any position along the orbit, right? For any of those positions, I can reevaluate this dot product by going into the tangent space, into the instantaneous inertial reference frame, and confirm my observation and get 0 again. So this dot product is always 0. Well, that reminds me of the characteristic of parallel transport. Okay, we recall that the tangent vector parallel transports along the geodesic. That's a definition of a geodesic. And we know also that if another vector parallel transports along the geodesic, it maintains the dot product with the tangent vector. Okay, So I see therefore that since this holds for any s, for any u as the orbit goes round and around, that s itself is going to have to be parallel transported, and there's the equation of motion then for s. So I just go back to my discussion of covariant derivatives, okay, and just write down that the covariant derivative applied to s is equal to 0, and then in the Schwarzschild coordinate system, this is what you have. So I'm just looking back at that, reminding myself about parallel transport, okay, and covariant derivatives. Just the most elementary discussion of those concepts, grabbing them from the introduction lecture on covariant derivatives. Okay, so now I want to just evaluate this thing. Okay, here's a differential equation. I want to solve it. I solve the differential equation for the orbit. I need the differential equation here. I want the time development of the spin as the spin is carried on a body which is orbiting the mass. So I look up the Schwarzschild metric and its Christoffel symbols, and of course I'm going to work in the plane theta equals pi over 2, because that as we've discussed for this parameterization is the most convenient way to look at orbits, right? We recall that orbits are planar in the Schwarzschild case, and so the theta equals pi over 2 is going to be true for all times. I start out the orbit in that plane, and it maintains it. And I'm looking at circular orbits, okay, so that the projection of the forward velocity of the body in the radial direction is equal to 0. It's a fixed r, fixed coordinate r, and a fixed coordinate theta. Okay, so I see that my velocity vector in the Schwarzschild frame has only two non-zero components. Okay, just the time component. Okay, just the time component and the phi component. Phi describing the rotation of the body around the mass. Okay, so that's going to simplify my kinematics a lot, and I'll get a slick solution because of that. Okay, and so I have to look up some of my Schwarzschild Christoffel symbols, okay, to plug them into here, and I don't have to look up all of them, okay, because all I need is it to be contracted against s and u, and in Schwarzschild coordinates, u only has a 0th component and a 3 component, right? The way we set things up, we had time, r, theta, phi, okay, so the third component of u will be different from 0. Okay, so therefore I just write it down and write down the bits that are non-zero. So ds0 satisfies this equation for parallel transport. Oh, and ds in the second direction, ds2 is equal to 0. In that particular case, the Christoffel symbols vanish. For the case of u having only a 0th component and a 3rd component. And then similarly, the differential equation for ds1 and the differential equation for ds3, the phi dependent. The theta dependence was particularly simple because many of the Christoffel symbols are 0 in that case, and in this case I'm picking theta equals pi over 2. Okay, so that's just a question of looking it up and cleaning it up. Okay. So I have a non-trivial differential equation because I'm working in curved space-time as usual. Okay. If I work in curved space-time, then these things are absent, right? And I just get that my spin maintains its direction. Okay, it moves by parallel transport, and so it maintains its direction in a Euclidean space. Mr. Newton. Okay, from our Schwarzschild discussion, I know U naught is to a factor of c. Okay, c is just the derivative of the coordinate time variable with respect to the proper time, and I look that up for a circular orbit. Remember, for a circular orbit. So remember we did that exercise, and we had this funny collection of 3 over 2 in the singular term for U naught, which told us that we couldn't have circular orbits, okay, for a radius that's less than 1.5 times the Schwarzschild radius. And we remember that was our first step on understanding circular orbits in the Schwarzschild environment. And we got stiffer constraints the further we went, but that was the first one that we ran into. Okay, so let's remember that. Okay, this is important. This fact is going to be important in this discussion. Okay, the amount of coordinate time that passes per proper time. Okay, the coordinate time is the time on a clock of an observer far away. The proper time is the time for the body itself. Put a starship captain on the body in orbit, and his wristwatch or her wristwatch tells that time. Okay, again, for Newton that would be 1. For us, here it is. Anything but 1. In fact, they're rather singular as we approach the Schwarzschild radius. If we're doing this around a black hole, and remember, I'm doing this generally. I'm doing strong gravity as well as weak gravity. So whatever. And then okay, and then I had the variable omega, capital omega. That was the time rate of change of the orbital angle phi. Okay, the orbital angle phi as a function of coordinate time t. Okay, and that's useful to parameterize my problem here, because I like to write u, the 4 vector velocity, as well. Its 0th component is just u naught, and then its 3rd component is d phi d tau. Okay, but it's more convenient in this particular case to parameterize my time development with t, the coordinate time, and so d phi by d tau is equal to, okay, d phi by dt times dt by d tau, and so I can pull out the u naught here and write the omega back in here. Okay, and so that's handy. These particular variables, I've used them before. I can steal from Schwarzschild how they behave as a function of r, and I reminded myself over here. Okay, this is basically the general relativity generalization of Kepler's 3rd law, as we discussed when we discussed orbits. So d phi by dt is just a function of r. For my circular orbit, it's just a constant. Okay, it's just a constant. The particle swings around in orbit with a fixed d phi by dt. It's given by the Schwarzschild radius, c squared, divided by twice coordinate radius to the cube, and then the whole thing square rooted. Okay, so let's try to clean up these equations. This equation describes the movement of the spin, but there's a constraint. The dot product of the spin with the velocity of the object is equal to 0, so I write that out. Okay, and again, writing that out is particularly easy, because for the contravariant description of the velocity, u has only 2 non-zero components, 0 and 3, and so I write those down here. Okay, I need the metric for 0, 0, and the metric for 3, 3, and that's what's shown here. Okay, well, good. So I'm given u naught, right? That's given. I'm in the Schwarzschild environment, so I know dt by d tau is this formula as a function of r. Okay, that's done. I know omega, d phi by dt, is a function of r. It's fixed, and so that's given as well. Okay, and so therefore this is a relationship between my 2 unknowns, s naught and s3. Okay. So we can solve, for example, for s naught in terms of s3, and eliminate this set of 4 equations down to a set of 3 equations. I'm more interested in getting the equations for the spatial components of spin. Okay, because that's the physics. Okay, when I do the solution, I see the ratio of u3 to u naught. Okay, so that's written down like this. That's just omega. Okay, that's just the rate at which the coordinate angle changes with respect to time. So that's a constant, a function of r, simple function of r for a fixed orbit of a fixed radius. I know what that is. Okay, and then I parameterize it in this way. I want to parameterize it in this way because I'm looking into precession. Okay, I want to know how the spin precess is relative, okay, to the motion of my satellite around the star. Okay, the motion of the satellite around the star is just given by d phi by dt. That's omega. Okay, so okay. So there's one frequency. Then I have the frequency of the rotation of the spin. Okay, and I want to know if those frequencies are the same. Okay, so anyway, so then if I can go back and solve for S naught in terms of S3, I can plug this into my parallel transport differential equation for S naught, and I find that it becomes the same equation as my parallel transport for S3. Well, okay, that's sort of not very surprising. The parallel transport idea was that it preserves the inner product of S and the tangent vector, and so I have that constraint, and the constraints don't give me any new information. They just say that both of those equations are the same. They're compatible. So I'm left with the equations, okay, for the other components. S1, that means S in the radial direction. Okay, S2, that's S in the theta direction. Okay, and S3, that's S in the phi direction. Okay, so there you go. Okay, and so I see. Okay, S2 is not interesting. Forget it. I see equation in S1 and S3, equation in S3 and S1. So I see coupled differential equation. Looks a lot like equations of precession that I know from Newton's world. And it's clear how I'm going to proceed. If I time differentiate this fellow, I'll get a second derivative of S1, first derivative of S3, but my other equation gave me the first derivative of S3, and it says it's proportional to S1. So that's the way to go. Okay, take this first equation and differentiate it, okay, and use the last equation to get a simple equation for S1, okay. Its time derivative, second time derivative will be proportional to itself. It'll probably satisfy sinusoidal motion, and that's what I expect. I expect the thing to rotate in some particular way. Okay, and remember, well, we'll make a picture of this. We'll make a picture of this in a moment, so we have it. But okay, and so I do that, and I choose to use the variable t. I want the solution in terms of the Schwarzschild coordinate time. I can always trade it for tau by the definition of u naught, but let's not. Okay, so here's u naught. Okay, down there, that's dt by d tau, and I can rewrite this then as ds1 with respect to dt, and similarly over here I can always trade. And so I do those trades, and I take these derivatives, and I get my differential equation for S1. Okay, like that, and then I leave this equation alone because once I have the solution for S1, I plug it in here, and I get the solution for S3. In particular, I see the solution for this fellow. I see that omega over u naught. Okay, remember u naught's a constant for an orbit of fixed radius. Is just a sinusoidal motion in that angular frequency, not omega, but omega over u naught. So I call that omega prime definition. Omega prime is omega over u naught, because that's the angular frequency of the precession of the spin. That's what the equation tells me. And then I can write it down. I know what u naught is, and I can see the formula here with the famous 1 minus 3 over 2 Rx divided by R. Okay, so I'll start with initial conditions that suit me. I'll take a spin, which is initially only has an S1 component. Was S1? S1 was meant radial, so I start with a spin pointing radially. Okay, and then I see that here's how the projection of the spin in the radial direction develops. It goes like cosine omega prime t. Okay, and then I come back, I take that, and I put that into my equation for S3, okay, and then I integrate this fellow up, and I see that S3 is equal to a minus, important minus sign, okay. This is the component of S in the theta direction, in the direction, okay, of that the particle particle sweeps out the orbit. And it goes, therefore, it goes like a derivative of S1, so the cosine becomes a sine. When I take the derivative, the cosine becomes actually a minus sine. Okay, and so I get this. Okay, so there you are. Let's make a picture of it. Okay, let's make a picture of it. That's shown here. So here's my body orbiting the mass at the origin. Okay, and so my body after a time t sweeps out an angle theta. So this is the plane of the orbit, and I'm going around in the phi direction. Right, I'm at fixed theta, a single plane. I'm going around in the phi direction. My body after a time t has a phi, which is omega times t. That's just the definition of omega. Okay, and then what about my spin? I'm showing my spin coming from the orbiting body. Okay, well it was rotating in the opposite direction because of that minus sign in S3. See that minus sign? Okay, in the minus sign. So the component along the radial, okay, was it just varies as cosine omega prime, and then the component in the phi direction. Here's the phi direction, right? As it sweeps along, phi direction goes like that, okay? And the projection of S in the phi direction is negative sine, so it's back in this direction. So it's sweeping in the omega prime direction in that direction, like that. Okay, and there's my solution. Okay, and we're done. Okay, well let's understand something very simple about this. We saw that in a Newtonian situation we didn't expect any precession at all. Okay, and I see, looking at this solution in a Newton's world, u naught, that's dt by d tau. Time is universal. For Newton, that's 1. Okay, so in that world, omega prime is equal to omega. So as the body rotates around, the spin relative to the radial direction rotates in the opposite direction. That's just a very complicated way of saying that the spin maintains the initial orientation, right? Okay, right. If omega prime in this picture is omega, then the spin is just maintaining its initial direction. Okay, but it doesn't quite maintain its initial direction. There is geodesic precession, right? Right. So we're orbiting with a geodesic with a little spin up there, and so this is called geodesic precession. I see it follows just from the basic principles of general relativity, even in the case of a static field. Okay, the angular difference after a time t. Okay, the angular difference here after a time t. Take the difference of the angles, multiply it times t, and that's the angular difference after a time t. Of course, go for one revolution. One revolution in coordinate time is 2 pi divided by the coordinate rate of change of the angular variable phi. Okay, 2 pi over omega, and so in fact, for one revolution, alpha is just t is 2 pi over omega, 2 pi, and then divided by omega, 1 minus omega prime over omega. So there's the solution. There's the amount of precession. Alpha gives you then the amount of precession in one revolution. Okay, and it's like this. Okay, okay. So I see, for example, if I had Newton and the Schwarzschild radius goes to 0, then of course alpha is equal to 0. Well, another way of saying that, of course, is that this square root is just the ratio of the observer's time far away to the proper time on the rotating body. Okay, for Newton you have absolute time, so that ratio is 1. So alpha is 2 pi 1 minus 1, 0. No effect. So it's interesting. Therefore, this is then a test of well, in this case of my Schwarzschild solution. It's a test of some notions of relativity. A comment about the experiment. This experiment was run by NASA, called Gravity Probe B. It measured omega prime to an accuracy of a few Okay, and it was able to do that because the effect is cumulative. You know, when we discussed the precession of the perihelion of Mercury, you can measure that because Mercury has been doing its thing for centuries, and the effect is cumulative. Okay, so after each orbit of Mercury, it precesses a tiny, tiny amount, and after a century, okay, you can get an observable accumulation. And so you look at that, and so that's exactly what gravity probe B did. It just looked for an accumulation of the precession of a finely tuned gyroscope on a satellite. And we saw also that omega prime is different from 0 because dt by d tau was different from 1. Okay. You might take that formula apart, or just go back. You know, the ratio. You know, it was a quantity that we got when we solved for the orbit, circular orbit of a test particle in the Schwarzschild metric, and okay, and we got this funny formula here: square root of 1 minus 3 Schwarzschild radius over twice the radius of the orbit. Okay, and you might take that look back at the derivation there, and you'll see that U0 gets really two physical contributions. Okay. Okay. So we're comparing the time on the satellite to the time of a stationary observer very far away. Okay. Well, one of the effects, okay, will be the redshift that relates that the the time of a clock at fixed position at the radius of the orbit to the clock of the observer very far away. But then in addition, that fellow is on a rotating orbit, so there's another contribution to the calculation of the relative rates of time. And when you calculate for both of those, then you get the funny factor of 3 halves. Okay, I'm just making the point that this factor here is not just the redshift. It's not just G00, okay? Okay, it has the physics of the motion of the orbit in it as well, which gives rise to this factor, this famous factor of 3 here, and it's easy to understand when you just realize that you're doing more than just the redshift verification in this experiment. You're doing redshift plus how orbits work in the Schwarzschild environment, and that delves into the equations of motion, the geodesic equation of motion of the orbiting satellite. So this is a deeper probe into general relativity than just a verification of the gravitational redshift. Okay, and that's all we want to say about that. So thanks.